All right, so today we're going to finish up our discussion of capacitors and dielectrics. We're going to save one section from chapter 24, which I'll talk about at the end, capacitors in a circuit. We're going to save those for chapter 25 and 26 when we actually do circuits, because it doesn't really make sense to talk about capacitors in a circuit if we haven't covered circuits yet. So we'll save one section from chapter 24 for next week. But okay, so for today, we're just going to finish up general capacitor and dielectric stuff. So what is a capacitor, first of all? So we have talked a little bit about capacitors when we were calculating electric fields. So a capacitor is just basically two conductors with equal and opposite charge. Now, they could technically be any sort of shapes, but we usually want nice, easy shapes. The most common is a parallel plate capacitor. So a parallel plate capacitor is just what it sounds like. It's made up of two equal opposite charged plates. They have some separation D between them. And now when we're doing problems, we're usually looking at like an infinite, we're assuming that it's infinite so that we can have a nice symmetric electric field in between. Obviously, we can't really have infinite plates with a perfect electric field. So when you're using like a physical capacitor, in between the two plates, like right in between here, this looks almost perfect, right? This is pretty much exactly what we've been doing, where you have a perfectly uniform electric field right in the center here. But then where the plates end, it obviously doesn't look as perfect anymore. So this you'll see called fringing effects. So this is what's called fringing. And in a lot of problems for capacitors, you'll see the problem says ignore fringing effects. So that just means ignore what's going on out here. So just ignore this stuff out here and just look in the center of the capacitor where our electric field is just perfectly uniform, and it's that sigma over epsilon naught. So capacitors are used in circuits and pretty much every electronic device. You can basically think of them like batteries, except instead of storing chemical potential energy like a battery does, they store electric potential energy instead. So capacitance, like I said, is, you can have a capacitor that's any shaped conductor. So if you have like two conductors that are both shaped like that or something, and they both have charge positive Q and minus Q, both the electric field and the potential of this setup will be directly proportional to that charge Q, that magnitude of the charge Q on each conductor. So the capacitance just measures the ratio of the magnitude of the charge on the conductors to the potential difference between them. And it's basically a measure of how much charge or energy can be stored in this configuration, which we'll see more later. So one important thing to keep in mind is that when we do capacitance, this is always positive. Our capacitance is always positive. So you always want to take the magnitude of the charges, and you always want your potential difference to be positive. So you want to always calculate, when you're calculating your potential difference between these two conductors or these two plates, you always want to do it in such a way that you get a positive answer. So you're never going to be plugging in like a negative potential difference here. And then capacitance is measured in farads. So a farad is just a coulomb per volt. So a farad is just a coulomb per volt. And then a farad is like pretty big. I think to get like a 1 farad plate, we're going to do a problem later where it's like you need like a mile long capacitor. So we're not really going to be using single farads. So just like with coulombs, you're going to be looking at very small numbers with farads. So just a reminder, you're going to be seeing microfarads a lot. So that is mu f. A micro is a mu. And that is 10 to the negative 6 is a micro. You'll see nanofarads a lot, which is NF. And that's 10 to the negative 9. And then you're also going to see picofarads. So you'll see picofarads, which is PF. And that's 10 to the negative 12. So these are the most common prefixes that you'll see, micro, nano, pico, and definitely memorize the 10 to the negative 6, 10 to the negative 9, and 10 to the negative 12. All right, now let's talk specifically about a parallel plate capacitor. So as we found yesterday, so a parallel plate capacitor, as I mentioned, you have the charges on each conductor is plus minus sigma, and they're separated by some distance d. So a couple lectures ago, we found the electric field in between a setup like this, and it's given by sigma over epsilon naught. And we also, in our last lecture, found the potential between these two plates, or maybe 2 lectures ago. The potential between these two plates, and it's given by the electric field between them times the distance between the 2 plates. So let's rewrite this a little bit. So we had that the electric field is sigma over epsilon, and we had the potential was the electric field times the distance between the plates. So we can rewrite sigma as the total charge on the plate divided by the surface area of the plate. So I'm going to replace sigma with total charge over area, since it's just a surface charge density. So I'm going to rewrite the electric field as Q over epsilon naught times A. And now I can also rewrite the potential in that way. So the potential I can rewrite as Q epsilon naught A times the distance between them. So I just replace the electric field here with this. And now my previous equation for capacitance was Q over V. So now let me replace this V with what I have here. So that's Q over Q epsilon naught A D. So this is all in the denominator here. So I can rewrite this a little bit. Let me move that here. So I can rewrite this. I can see that my Q's cancel, right? My Q's actually cancel here. And I can rewrite this as epsilon naught times A over the distance between the plates. So now this is interesting. So we are going to have that. This is interesting because that means that I can rewrite my capacitance in terms of just geometrical quantities, right? My capacitance is completely defined here by the area of the plates and the distance between them. So remember, each plate is going to have the same surface area since they're the same size plate. So my capacitance is completely defined by my geometry. And it actually doesn't matter what the charge or what the potential difference between my plates are. So capacitance is really a geometrical quantity. It describes basically the geometry of your system and that geometry's ability to store energy. So let's do a simple example now. So we want to find the area of a plate of a 1 farad capacitor with separation of 1 millimeter. So our capacitor is 1 farad. The distance between them is 10 to the negative 3 meters. And we want to find the area of these plates. So our capacitance, as we found in the last slide, was epsilon naught times A over D. So we can rearrange this formula to get for A, right? So I can just write that A is equal to CD over epsilon naught. And now I can plug in my numbers. So my area will be equal to the capacitance is 1 farad, we said. The distance between the plates was 10 to the negative 3 meters. And then epsilon naught is 8.85 times 10 to the negative 12. And this number comes out to 1.1 times 10 to the 8 meters squared. So how big is an area of basically 10 to the 8 meters squared? Well, to get something that's about 10 to the 8, if you had an area of something, let's say like a square, that was 10 to the 8, you would need each side to be about 10 to the 4, right? That way when you did length times width, you would get 10 to the 8. So 10 to the 4 meters, we can think of as 10 times 10 to the 3 meters, which is 10 kilometers. And 10 kilometers is about 6 miles. So this would be a really big capacitor to just get a capacitance of 1 farad. And since our capacitors are normally very tiny, like you have capacitors in your phone, those are obviously not 6 miles long, the capacitances of those capacitors is going to be super tiny, which is why we're using those picofarads and 10 to the negative 12 and stuff like that. Okay, now let's go on to another more realistic example. So here we have the plates of a parallel plate capacitor in a vacuum are 5 millimeters apart. So we have the distance between them is 5 times 10 to the negative 3 meters. And the area of the plates is 2 meters squared. So their area is 2 meters squared. A 10 kilovolt potential difference, 10 kilovolts, oops. That's going to be 10 times 10 to the 3 volts, is applied across the capacitor. Compute the capacitance, the charge on each plate, and the magnitude of the electric field between each plate. Okay, so let's do first the capacitance. So C will be equal to, we can write it, since we have the area and the distance, we can just write it using this form for the capacitance. So let's plug that in. So we have epsilon naught is 8.85 times 10 to the negative 12. The area is just 2. And then the distance was 5 times 10 to the negative 3. So this number comes out to 3.54 times 10 to the negative 9 farads, or you can write that as nanofarads. So either way is fine. Okay, so this is our capacitance. So this is a much more realistic capacitance, even though it's still a pretty big capacitor. 2 meters squared is pretty big. So now let's do part B. We want to find the charge on each plate. So now we can use this formula. So since we have the capacitance now, we were given the voltage between the plates, we can find easily now the charge. So the charge will just be given by C times V. So our capacitance is 3.54 times 10 to the negative 9. The voltage we can write as 10 to the 4, because it was 10 times 10 to the 3. So that comes out to 3.54 times 10 to the negative 5 coulombs. So this is our charge on our plates. And now we want to find the magnitude of the electric field between the plates. So we can, remember we had written our electric field, the surface charge divided by the epsilon naught, we could write as the total charge on our plates divided by the area of our plates. So we just rewrote the surface charge there. So now here we have Q, we've got A, we can just plug these in and find the electric field. So we're going to plug in our charge is 3.54 times 10 to the negative 5. Then divide that by 8.85 times 10 to the negative 12. And then we have the area of our plates was 2 meters. And we get our electric field here is 2 times 10 to the 6 newtons per coulomb. So this is our electric field between the plates. Okay, so this was a relatively straightforward example. So now let's talk about how capacitors store energy. So when capacitors store energy, they have to be charged first, right? Because if we have two plates with some charge plus and minus Q on them, that charge has to get there somehow. So that's called charging a capacitor, and that's when you put energy into the capacitor. So like I said, capacitors store energy. Well, that stored energy has to come from somewhere, and it comes from when you charge the capacitor. So the energy that you put in to charge the capacitor, to put that charge on those plates, that's the energy that will be stored in your capacitor, and that's the energy that will be released whenever you choose to release it. So we'll see when we do circuits how that energy is released through the circuit. But one example of a capacitor releasing energy is like if you have a flash camera, the flash energy is stored on a capacitor, and when you press the button, it releases the energy. So we'll talk more about that when we do circuits. So basically, just a little bit of circuits. We have let's say we have some battery here, so that's a battery, and then we have a capacitor. So this is how we're going to draw capacitors when we do circuits. So we've got a little circuit here. We've got some wires, a battery, and our capacitor. That battery will make a current flow through our circuit, and charge will collect on each of these plates. So we'll have like a positive Q and a negative Q on these plates, and that is charging the capacitor. So it starts at 0 charge. So our capacitor starts with 0 charge on the plates. You turn the battery on, the charge begins to build up and collect, and now your capacitor is charged with plus minus Q. So that's what it means by charging a capacitor. Now we learned when we did potential energy that the work done by an external force is equal to the potential energy of that configuration. So the work that I had to do, or the battery had to do, to charge the capacitor is equal to Q times V, where this is the charge and this is the potential difference between our plates. Now to find the total work done, since you're not just putting one single little electron or one single little proton on your plates, you're putting a lot of them to get your capacitor fully charged, you have to integrate from 0Q to capital Q, which is the total charge on the plates. So you can just take this equation and just integrate. So we rewrote here, we're integrating over Q, so we have our little differential work, V times dQ. We can rewrite V as Q over C from our equation here. So we rewrote V as Q over C, and then we're integrating with respect to dQ. So just integrate this equation, integrate Q dQ from 0 to capital Q, and you get Q squared over 2C, right? Because this integral will be 1/2 Q squared. So this integral will come out to 1/2 Q squared. Okay, so this isn't that important. This is just where the equation comes from. We're not really going to be doing any integrals like this for capacitors, but this is just where the equation for the energy stored comes from. All right, so that's how we charge a capacitor. Now, there's a couple different ways that we could write the energy stored in a capacitor. So we just found this way, and again, we denote the potential energy for our capacitor as U, capital U. So we just found this first way where we had Q squared over 2C. Now I can get rid of my Q there, because remember C is equal to Q over V, which means that Q is equal to C times V. So I can swap out this Q here with C times V. So this will be CV squared over 2C, which is equal to C squared. Let me write it this way. So then I'll just distribute my squared. I can see that my C's will cancel. So now I can rewrite this as 1/2 CV squared, which is this equation here. And now if I wanted to get rid of the C instead and write it in terms of the charge and the potential, I can just swap out this C for Q over V instead. So I could also write 1/2 Q over V, V squared, and we can see that that comes out to 1/2 Q V. So these are all equivalent, and obviously depending on what your problem gives you, if they give you the charge and the potential, you'll want to use this form. If they give you the charge and the capacitance, you'll obviously want to use this form. So it's just a couple different ways to write the same thing. So now we can talk about the energy density in a capacitor. So if we have a potential energy stored in the capacitor, that means that the energy is stored between the plates. So we have our positive plate and our negative plate, and we have some electric field going from the positive to the negative plate here. And when we have potential energy stored here, it's stored between the plates, so it's stored in here. So we can find the energy density in our capacitor, and all we have to do is just divide the total energy by the volume. So we just find the energy density by taking the total energy, capital U, and divide by the volume. Well, what's the volume? Well, the volume is just going to be our length times width times height. We know our length times width is just the area of the plate, right? The area of either of the plates is just the length times the width. And then the height is just going to be the distance between the two plates. So this is D. So our volume is just equal to A times D. So we just divide our total potential energy by the area and the distance between our plates. And that will give us the energy density. And now you can get from this equation to this equation from the equations that we already had, where we know the potential between the two plates and we know the electric field between the two plates. So see if you can get from this equation to here using what we already know about capacitors. So the energy density of our capacitor is given by this 1/2 epsilon naught times the square of the electric field between them. And we just take the magnitude of the electric field here, since this is just a scalar. So the energy density is obviously going to be measured in joules per meter cubed, since it's energy density. And now one interesting thing to note here is that you might say, like, well, where is the energy actually stored? Like saying the energy is stored between the plates, well, nothing's between the plates, right? There's just vacuum between the plates. But the energy is actually stored in the electric field, which again might sound real, kind of weird, and it is. But the energy is stored in the field, even though it's in a vacuum. And this equation actually holds for any electric field configuration. The electric or the electromagnetic field stores energy in the field, and it can transport energy. That's why when you go outside, you can feel the sun on your face, because the electromagnetic waves from the sun are transporting energy from the sun to your face. So electromagnetic waves can transport energy, and they can store energy in the field. So when you take like 7C, you'll talk about energy transport in an electromagnetic wave, and you'll see this equation again for just a general electromagnetic wave. So that's one thing that's kind of weird. We're not used to waves transporting energy without a medium, but the wave itself is the medium. Maybe you could think about it that way. So that's just another weird thing about the electric field. When we insert a dielectric into a capacitor, a dielectric is an insulator because the charges can't move. Even though the charges can rotate, like we mentioned in our last lecture, the charges can rotate, but they can't move. So that means a dielectric is considered an insulator, since our charges are fixed. So when we insert a dielectric into a capacitor, we have our initial capacitance C0, where that's just a vacuum. There's nothing in between our plates. We insert a dielectric between our plates here that fills up the whole separation between our plates, and it will increase the capacitance by a factor equal to the dielectric constant. So we'll just multiply our original capacitance by the dielectric constant. Okay, it will also, so the way that it increases the capacitance basically is that it decreases the potential between your plates, and it also decreases your electric field between your plates. So this is assuming that we're holding our charge constant on the plates. So you charge up your capacitor to some charge Q, and it stays that charge Q. We'll see in later lectures what happens if we change the charge on it, but for now we're keeping our charge constant at Q, and if you keep your charge constant and insert a dielectric between it, remember from yesterday when we did Gauss's law in dielectrics, our electric field between the plates without a dielectric is sigma over epsilon naught. Now, let me just rewrite this for capacitors. That would be Q over A. Now, if I insert a dielectric here, my electric field becomes K epsilon naught, right? Where this is the, this is epsilon. So now I can see that my electric field actually decreased by an amount K, right? This was my original electric field here. So now my new electric field is 1 over K times that original electric field. So my electric field decreased by a factor of K, and the same thing happens with the potential. And just as a reminder, that happens because when you insert your dielectric into an existing electric field, so between the plates you have the electric field going from the positive plate to the negative plate, all of the positive charges of the dielectric are going to want to align with that negative plate. They want to go towards the negative plate. And then all the negative ends of the dipoles are going to want to align to the positive plate. So they're going to get pulled towards the positive plate. And so then this arrangement of your dielectrics, of your dipole, sorry, will create an opposing electric field. So this creates an electric field that goes this way. So it will create an opposing electric field to the one that's created by the two parallel plates. And so it will decrease your total electric field. And as I said yesterday, the electric field created by your dielectric, the opposing electric field, is much, much weaker than the one created by the plates, but it still decreases the total electric field. Okay, and then we can also see that this is going to decrease the energy density of your capacitor. Now again, this is important. In your book, when they go over this, they don't make it clear that they're holding Q constant. So if we hold Q constant, and also in your book it looks like the energy density is increasing, but it's really decreasing. I'll show you why. So in your book, they write this as 1/2, let me write it over here. They write the energy density with the dielectric as 1/2 K epsilon naught E squared. And now you might look at this and you say, well, clearly if K is bigger than 1, the energy density has increased. So the dielectric is actually increasing my energy density. But since we're holding Q constant and we insert a dielectric, that means that our electric field is decreasing, right? So our electric field, so we replace epsilon naught by K times epsilon naught. So we have K epsilon naught, but our electric field has also decreased. And our electric field has decreased by a factor of K. So our new electric field is E over K, and then we square that. So we get 1/2 K epsilon naught, E squared over K squared. We can see that our K here cancels, and we're left with 1/2 1 over K epsilon naught E squared. This is our original electric field. So you can see that overall, your electric field actually, your energy stored actually decreases by a factor of K when you insert a dielectric. And here, this electric field is the new electric field with the dielectric. So this would be, this E here would be like sigma over epsilon, which is sigma over K times epsilon naught. All right, now let's do some examples of different shaped capacitors. So I mentioned that technically a capacitor can be any shaped conductors. We're obviously only going to be doing like nicely shaped ones, but you could have any crazy shape you want. So let's do a spherical capacitor. So if we have a spherical capacitor, let's say we're going to have two concentric spheres like this, so one over the other. We'll say that the inner radius is A, the outer one is at B, and the inner sphere or shell, whatever you want to call it, has a positive charge on it of plus Q, and the outer shell has minus Q total charge. So how do we find the capacitance of this setup? So let's write our Q over V, C equals Q over V. Now we have Q because I gave it to you. I said that each shell has plus minus Q on it. So now we need to find the potential difference between these two spheres. So how are we going to do that? Well, we have to think back to how we calculate potential. And we had two different ways of doing it, right? We could integrate over dq, or we could take the integral of the electric field. Now integrating over, if I was to calculate my potential using the integral, I don't want to do that in this problem because that looks like an annoying integral to do. But because of Gauss's law, I immediately know the electric field in between these two spheres, right? So doing the potential and calculating it as the integral of the electric field is actually going to be really easy because I'm only worried about the space in between the plates, right? Now here, I know right away that there's no electric field anyway. And I know the electric field in between the plates, right? And I know it's going to be that of just a point charge. Because from Gauss's law, I know that this sphere will behave as a point charge once I'm outside the sphere. And I know the electric field of a point charge is just going to be Q over 4 pi epsilon r squared. I know it's going to be in the r hat direction since this is a positive Q. And I know that this charge out here, this sphere out here, won't contribute to the electric field in here since it's outside my Gaussian surface. So I know the electric field in here already, so this is going to be a really easy integral to do. So let's calculate the potential between the two plates. And I don't need to care about inside the conductor. I don't need to care about outside the two conductors. All I care about is in between that radius A to B. So let's do this integral. So our potential, so we're going to integrate from our outer sphere to our inner sphere. Our electric field is Q over 4 pi epsilon naught r squared. We're integrating with respect to dr. Let's pull out our constants. We've got a negative Q 4 pi epsilon naught. We're integrating 1 over r squared dr. This integral, I know, is going to become 1 over r, a negative 1 over r, right? So I can cancel out my negatives here, right? So I've got two negatives there. And this is being evaluated from b to a. So that is equal to 1 over a minus 1 over b. And now I can plug everything back in. So this comes out to Q over 4 pi epsilon naught, 1 over a minus 1 over b. And now I can find my capacitance. So my capacitance is just Q, so I don't have to do anything with that, I already have Q, over V. So that's going to be Q over 4 pi epsilon naught, and then I have 1 over A minus 1 over B. My Q's obviously cancel right away, so I'm left with 4 pi epsilon naught over 1 over A minus 1 over B. But this is a little bit ugly. I don't want to have a fraction of fractions. So let's just rewrite the denominator here. Let's rewrite this 1 over A minus 1 over B. Get a common denominator for them. So I'll multiply this one by B over B. And I'll multiply this one by A over A. So I can see that this will come out to 1 times b minus 1 times a is just b minus a, and then my common denominator is a times b. So I can rewrite this denominator as 4 pi epsilon naught b minus a over b, which becomes 4 pi epsilon naught a over b minus a. And that is my final answer for my capacitance of a spherical capacitor. And now you don't have to do this final step, like that's not necessary. It's not wrong if you leave your answer like this. It's just generally you don't want like fractions in your fraction. And this way also it's clear that my capacitance is positive because my radius b is bigger than my radius a. So this denominator here will definitely be positive, so my overall capacitance is definitely positive. Whereas here, it's a little bit obscured that this is actually a positive quantity. All right, in your book also, they do a cylindrical capacitor, so that's a really good, and we might do it for discussion, but that's a really good problem to know how to do as well. So definitely know how to do the capacitance for a sphere, and then also try for a cylinder as well. All right, now let's do one last example. So here we have a parallel plate capacitor with a dielectric. So we have our dielectric has an area of 2,000 centimeters squared. So let's write that down right away. So we have our area is 2 times 10 to the negative 1 meters squared. And are 1 centimeter apart. So the distance between them is just 10 to the negative 2 meters. We connect the capacitor to a power supply, charge it to a potential difference of 3 kilovolts. So that just means our potential difference between our plates is 3 times 10 to the 3 volts. and then disconnect the power supply. We then insert a sheet of insulating plastic material between the plates, completely filling the space between them. So we insert a dielectric, since plastic is a common dielectric. We find that the potential difference decreases. So this was our original V. The potential difference decreases to 1 kilovolt. So that's just 10 to the 3 volts, while the charge on each capacitor remains the same. So our charge stays the same as we said before. Find the original capacitance and the magnitude. Okay, so let's find the original capacitance. So let's first just find the capacitance. So the capacitance is going to be given by epsilon naught A over D. Since we were given A and D already, let's obviously use that formula for the capacitance. So we're going to have 8.85 times 10 to the negative 12 times the area, which was 2 times 10 to the negative 1. So we can just write that as 0.2. And then the distance was 10 to the negative 2. So that comes out to 177 times 10 to the negative 12 farads. So that's 177 picofarads. So this is our capacitance of our capacitor. So now we want to find the magnitude of the charge on each plate. So so to find the magnitude of the charge on each plate, we can just use this equation that the capacitance is Q over V, and we can see that Q here is given by C times V. We just found the capacitance and we were given the voltage, the original voltage. So this will be the original capacitance and original voltage. So our capacitance was 177 times 10 to the negative 12. The original voltage was 3 times 10 to the 3 volts, 3 kilovolts. So we have 3 times 10 to the 3 volts, and this comes out to 5.31 times 10 to the negative 7 coulombs. So this is our charge on each of our plates. And now for part C, we want to find the capacitance after the dielectric is inserted. So after the dielectric is inserted, remember our capacitance is going to be bigger than our original capacitance because the dielectric will increase the capacitance of our capacitor. So how do we figure out the new capacitance? Well, we can figure out the dielectric constant quite easily because remember the dielectric will decrease the potential between the plates if you keep the charge constant by a factor of K. And we already know what the potential was after the dielectric was inserted, and we know what the potential was before the dielectric was inserted, so we can very easily solve for K here. So our potential after the dielectric was inserted was 1 kilovolt, and our potential before the dielectric was inserted was 3 kilovolts. So you can clearly see that K is going to be 3. So this is going to be 3. So K is equal to 3. So now we can just plug that into this equation and solve for our capacitance after our dielectric hasn't been inserted. So the capacitance after the dielectric is just the dielectric constant times the original capacitance, which was just 177 times 10 to the negative 12. And that comes out to, so this comes out to 5.31 times 10 to the negative 10 farads. So this is our capacitance after the dielectric is inserted. Now you could also, you can do these different ways. So I just happened to do it by finding the dielectric constant first. You could also do it because you have the total charge on the plates and you have your initial potential. So you could do it that way as well, and you would get the same answer. So then for part D, we have to find the dielectric constant. So we already found that. So part D is what we already found. So K is just equal to 3. And then the permittivity epsilon of the dielectric. So that all we have to do, the permittivity is equal to the dielectric constant times the electric constant. So we just have to times 3. Oops. So we just do 3 times 8.85 times 10 to the negative 12. And that comes out to 2.66 times 10 to the negative 11. So this is our permittivity for our dielectric. It's just the dielectric constant times epsilon naught. And now let's see part F, the magnitude of the induced charge on the dielectric, the bound charge on each dielectric surface. So let's start here. So the induced charge, the magnitude of the induced charge on each surface, we found the formula for this yesterday. So yesterday we found that the induced or bound charge was given by the free charge times 1 minus 1 over the dielectric constant. So again, the free charge is the charge that's on your plate. So this is like plus minus Q over A. And then the induced charge is the induced little dipole surface charge from your dielectric that's actually on your dielectric surface. So since the dielectric doesn't change the magnitude of this Q, and it obviously doesn't change the area of our plates, the same equation holds for capital Q. So here, QF, we can just insert the charge that we found when we found the charge on each plate here. So this is just the charge on each plate. So we have 5.31 times 10 to the negative 7 coulombs. So we just insert that here. So we have 5.31 times 10 to the negative 7. Yeah, 7 coulombs times 1 minus 1 over 3. 1 minus 1 over 3 is just 2 over 3. So we just multiply our charge by 2/3, and we get 3.54 times 10 to the negative 7 coulombs. So this is the magnitude of the induced charge on the surface of our dielectric. Okay, now we have, so we found part F. Now part G, the original electric field between the plates. So the original electric field between the plates, we're on part G now. So the original electric field. So there's a bunch of different ways you could do this. I think the easiest way, remember the potential between the plates is just the electric field times the distance. So to find the electric field, the original electric field, we can just divide the original potential by the distance between the plates. So this will just give us, the original potential was 3 kilovolts, and the distance between the plates was 1 centimeter. So this will just come out to 3 times 10 to the 5th. And that is our electric field. Okay, let's see. Oh, and that's volts per meter. Or newtons per coulomb. Okay, so then our last part is the electric field E after the dielectric has been inserted. So this part is straightforward. So the electric field after the dielectric has been inserted, we know that the dielectric is just going to decrease the electric field by an amount equal to the dielectric constant. So this is just going to be equal to the original electric field divided by K. So we just do 3 times 10 to the 5th divided by 3, which is just 10 to the 5th. So we just have 10 to the 5 is our electric field after the dielectric is inserted. And that's it. Okay, so that's it for today. Like I said, we're going to be skipping the section on capacitors in a circuit, and we'll cover that next week when we do circuits. So that's it for today, and I will see you guys next week.